Okay, so last time we were discussing performance issues in programming, and today we are going to continue in that direction. So the last thing that we were discussing on last Wednesday was this Fibonacci number generator. Practically, Fibonacci numbers are a sequence where each number is the sum of two previous numbers. So the function f of n is f of n minus 1 plus f of n minus 2. And we said that when we write program in this way, this is the most elegant non-procedural program that you can write. It is short, single line, and gives correct results. So it is a beautiful program, which is, of course, tragically inefficient because we have that for computing this f of n, we have to compute f of n minus 1 and f of n minus 2. Of course, when you compute f of n minus 1, you also repeat f of n minus 2. So this f of n minus 2 is going to be repeated twice, and so on and so forth. So you have something like a binary tree, not balanced and not perfect, but it is rather poor. So you have that time for performing this operation, t of n, is time for performing n minus 1 plus time for performing n function of n minus 2 plus a little bit of negligible time for one if statement that is here inside to decide are you going to return n or to call these two functions. So we have that approximately t of n is t of n minus 1 plus t of n minus 2. When you take this functional equation and solve it by inserting two constants, c times g to n, you get that g is 1.6. So t of n is O of 1.6 to n. It is not 2 to n, but is equally bad. So we said that this for, say, 32 arguments takes 7 minutes on a machine that has 1 million operations per second. So that is very, very slow. If you write this program not in recursive, but in procedural way, by having three variables, 0, first, and second, then you can write the program that has one single loop going from 2 to n. Second is first plus 0, and then you shift them. 0 becomes first, first becomes 0, and second becomes first, and then you again compute second is first plus 0. When you do that, then you have a program that is ugly. This one is certainly not beautiful. Has three variables, first, second, and third, or 0, first, second, that are not visible in the statement of the problem. Nobody is telling you that there is first, second, and third. There is also counter I, which is not visible here. There is no counter in the statement of the problem. So this is a typical procedural program. You make the procedure based on auxiliary variables, and what you get as the result is linear program O of n that works in few microseconds. It is very difficult to measure the time because it is so fast. The program is procedural, it is ugly, but it gives you performance as opposed to this program, which is non-procedural, very elegant, short, and has nothing other than what you have to mathematically specify, but it is terribly slow. So we have also algorithms that have higher complexity than exponential. This is factorial algorithm, and traveling salesman is one of them. And such algorithms, you cannot write programs that work directly in that way, but you have to have something that is faster, but approximate. Okay, so I want to show you a few more examples, and here is one example that is creating digits from 1 through 6 with equal probability. So this is like a 6-sided die simulator. So you are throwing 2 dice if you want, and getting combinations of 1 through 6 and 1 through 6. How to make such a generator? Of course, we use RAND. RAND is random number generator that is part of standard library.h, or in namespace standard, you find RAND generator, and what you are getting from that generator is an unsigned integer between 0 and maximum value RAND max. And then when you take this integer modulo 6, you get value 0, 1, 2, 3, 4, 5. So from 0 to 5 with equal probability. So add 1 to that 0 to 5 and you get 1 through 6. So return 1 plus RAND modulo 6. And this is going to create the sequence of digits 1 to up to 6. If you want a binary sequence like flipping the coin, then you take RAND modulo 2 and you get 0, 1, 0, 1, 1, 0, 0, 0, 1, etc. Random binary sequence. Now, I want you to now use this RAND generator to create a random digit generator. So the assignment is generate digits 1, 2, 3, 4 with probabilities 10%, 20, 30, 40%. So I have to have a generator that with probability of 10% will return number 1. With probability 20%, digit 2. With 30%, 3. And with 40%, 4. So these 4 are going to be 4 times more frequent than 1s and 2 times more frequent than 2s. So here is my program. Random digit 1, 2, 3, 4. It is a void program, returns an integer. And then what I have here is that I'm going to compute this double precision value u, which is RAND divided by RAND max. RAND max is a constant that is stored in the same library as RAND. So you don't have to tell anything, but just to divide RAND by RAND max. When you do that, you get U, which is uniform random number between 0 and 1. So like probability between 0 and 1, it is a real number in that interval. So since the value is uniformly distributed, with 10% of probability, I have that this uniform random number is less than 0.1. So if u is less than 0.1, I'm going to return 1. And this happens in 10% of cases. In 20% of cases, this number will be between 0.1 and 0.3. So this is 0.2 that is difference. In 20% of cases, I'm going to return 2. So I have, if u is less than 0.3, return 2. Now, this happens in 20% of cases. In 30% of cases, the value will be between 0.3 and 0.6. If u is less than 0.6, this happens in 30% of cases, I return digit 3. And in all other cases, in 40% of other cases, I return 4. So this is the program, very simple, that returns 1, 2, 3, 4 with these probabilities. 40% of them are 4, 20% of 2, 30% 3, and 10% 1. However, this is version A. I can write version B of that program, and this is this one here. So I can say, you know what, I have this u that is between 0 and 1. In 40% of cases, u is going to be less than 0.4. Therefore, I'm going to return 4 in that case. If u is less than 0.7, therefore, it is between 0.4 and 0.7, this returns in 30% of cases. Therefore, return this 3. If u is between 0.7 and 0.9, this happens in 20% of cases, I return 2. And in all other cases, in 10% of cases, I'm going to return 1. And this works exactly the same as version A. So the question is, which version is better, A or B? And for what reason? Can somebody tell me? So we can intuitively see which one is better rather easily, but we can also do that mathematically if you want. So the number of statements that I'm executing is 1 here always, plus here is the random number of statements. So I have this one statement that occurs with 40%, this is with 30%, I have 2 of them, and so on and so forth. So I can write like this, that in the first case, with 10% of probability 0.1, I have only one statement that I have here. Because with probability 0.1, I'm going to return 1. And we'll have one statement out of these 1, 2, or 3, or 4 of them that I can execute. So with 10%, I have 1. With 20%, I have 2. With 30%, I have 3. With 100%, I have 4. So what's going to be here is that 0.1 times 1, 0.2 times 2, 0.3 times 3, and 0.4 times 4 gives me that this first program has, on the average, 3 statements. So the average number of statements is 3. In the second one, this one here, the average number of statements is 2, because I have the most frequent event first. So in 40% of cases, I'm going to have only one statement, return 4, and I go out. I never go here and here and here. Then with 30% of cases, I'm going to have 2 statements here. So 30% times 2, 20% times 3, and 10% times 4 lines of code. Therefore, the second has 2 statements. So you have that by changing order of these statements, you can go from 3 to 2, which is practically 33% difference in performance, 33% slower is A than B, if I write that in the wrong order. So this is a typical programming assignment. So programmers should understand that it is not good to have the least frequent case first and the most frequent case last. The common sense tells you, hey, put the most frequent case first and the least frequent case last. In that case, you are going to have less if statements that you have to execute. And this is what procedural programming teaches us to do. Try to be aware of performance, and performance awareness will tell you that you write this program that returns first 4 and not this program that returns first 1 and last 4, because this is going to be slower. So there are plenty of examples where the speed can be obtained by modifications of programs, small modifications of programs. I call that performance awareness. And this is the soul of the procedural programming. That's what we are doing now. So one thing that is very characteristic in this area is what is called the brute force programming. So what is the brute force programming? And let us fight against the brute force programming. Brute force programming is defined as approach where algorithm is very poor. Efficiency of algorithm is low, but computers are fast, and still solutions will be generated in acceptable time. So we don't care about performance. We say this generates results, it takes a long time, etc. Brute force approach is intellectual bankruptcy. Intellectual bankruptcy. That is when you have this kind of program. So you can use it for quick and dirty solution of some things that you do when nobody is watching. You do that for yourself. In 20 minutes, you have to create some solutions. So you don't care, are you sorting in efficient way or you're using select sort, that is 3 lines quadratic sort. You don't care about that because you are focused on other things. This is acceptable there, but absolutely not acceptable if you are a professional programmer making program for market that you want to sell to somebody. This is absolutely unacceptable. So I want now to fight against brute force approach. The simplest way to see brute force approach is to see the time complexity. O of constant, O of log n, O of n, O of n log n square, n cube, etc. So these are increasing sequence of complexities. And of course, what is not acceptable is to use quadratic algorithm if it is possible to have linear algorithm. Obviously, the first step in procedural programming is to find the algorithm of the lower order of complexity, and then to write it in a way that is the most efficient. So I want now to show you today several examples that will illustrate this conclusion and show you how programmers can improve performance without changing algorithmic complexity. So a typical brute force example I got when I was teaching 210. And I said, you know what, there are in triangle three sides, A, B, and C. So Pythagoras theorem tells you that A squared plus B squared equals C squared. You know that, okay. So the famous numbers A, B, and C that everybody knows are 3, 4, and 5. So 3 squared plus 4 squared equals 5 squared. So 9 plus 16 is 25. Also, 6, 8, and 10. When you multiply this by 2, you get 36 plus 64 is 100. Okay. So the assignment that I gave on exam was write a program that will tell you all these values A, B, and C that are less than 100. So if you have that A, B, and C, so triangles that are less than 100 and have, of course, integer sizes, write a program that will find all these triples that are giving A squared plus B squared equals C squared, but A, B, and C have to be less than 100. Of course, you have an infinite number of such triangles, an infinite number of such triples. So without any particular mathematical knowledge, I want to write as a programmer a program that will tell me what are these triples. So when I write such a program, here is what I get. 3, 4, and 5 is such triple. So 9 plus 16 is 25. Of course, 6, 8, and 10 is also such triple. But I, of course, never knew that 57, 76, and 95 are also such triple. So what I learned from this little program is that there are 50 solutions starting with 3, 4, 5, and the last one that is less than 100 is 65, 72, and 97. Okay, so 65 squared plus 72 squared is 97 squared. If you go above that, you are above 100, and we are not interested in that. So I have to write a program that is generating this 50 solutions. So the question is, how many tests are necessary to generate these results? So I expected to find a program that will be reasonable that is generating this. And here is the first solution. Actually, unfortunately, the most frequent that I got in 210. Here is the program. You say I have A that is going between 1 and 100, 1 and 99. B is between 1 and 99, and C is between 1 and 99. So I'm going to make 3 loops, A, B, and C loop. We'll create all combinations of A, B, and C, and then we'll ask for this combination, is A squared plus B squared equals C squared? Now, if A squared plus B squared equals C squared, this is such a triple, and I'm going to display that. So A, B, and C will be displayed, and I'm going to have lines that will include these triples. Is this working? Of course it is working. It gives me all triples. I also wanted to see how many tests I have. So I put one variable called tests, which is a counter of this test. Test is 0 and incrementing test in each of these loop execution. So the number of execution is 99 times 99 times 99, which is 1 million practically, 970,000. If you run this program, which is obviously correct and obviously generates all results, you immediately see that something is wrong. And what is wrong is that you get not 50 results, but you get 100 results. For what reason? Well, the reason is simple and trivial. You get 3, 4, and 5, but you will also get 4, 3, and 5. So you have the permutation that you get of that. So you see that you do things unnecessarily too many times. So practically, is this program correct? Yes. Is it good? Of course it is not. It is terrible. For what reason? Test cases include both cases where A is less than B and A is greater than B. So each result is generated twice. I don't need twice the same result. I need result only once. That's the first problem that is wrong. Second problem, A square plus B square is C square. Well, in that case, you know from triangle that C must be greater than A and C must be greater than B. Do you agree with that? Of course, but we test all possible C's. So even C's that are less than A and less than B. So this is meaningless and you should not test these C's. Also, this C must be less than A plus B. But we are also testing those that are greater than A plus B. You immediately see that you have this case where C is greater than A, C is greater than B that we tested, and also in triangle C is less than A plus B. Therefore, the program test should not include cases where this is satisfied, but only those where C is A greater than A plus B. So the number of tests is unnecessarily too big. And that's what I expected that people will do. So if you say, I'm going to check A that is less than B, and then this B is less than C. So I'm writing the loop first A from 1 through n minus 1. So from 1 through 99. B is going to go from A plus 1 to 91 to 99. And C is going to go from B plus 1 to 99. So I keep this here. The number of tests is dropping from 1 million to 156,000. So this is now much better. And it is the same complexity, same 3 loops, everything is the same, but it is not shameful. This is without the use of brain. And this here is with little bit of use of, shows some little bit of understanding. Then I can also say, you know what, if I have triangle A square plus B square less than C square, which is less than n square, then B must be less than n square minus A. So if I put here the border for this B loop here, I reduce that from 156 to 148. A little bit of improvement, but still some improvement. Then I can say, you know what, C must be less than A plus B. So do this the same way, but put inside that C is less than A plus B. Now the number of tests drops from 148,000 to 68,000 something. So this is much better than 1 million at the beginning. And eventually I can say, you know what, I'm not going to have 3 loops at all. I'm going to make 2 loops. I'm going to change, to have A going from 1 through n, and B going from A plus 1 to this final value. And then I'm going to compute C, which is square root of A square plus B square. So this C can be integer or not integer, but if I define C as integer, it is going to truncate this to integer value. So if A square plus B square is C square, this is the case where this is satisfied. And therefore, I have a result made with 2 loops, not with 3. This is still a kind of brute force approach. I'm testing all components, but it is not shameful. Shameful is the first one. This one has 3,840 tests. So we started with almost million here, and then reduced to 156,000, 48,000, 68,000, and then 3,000. So it is done without using any mathematical theory. There are mathematical theories how to create Pythagorean triples. And of course, I don't know any of them to apply in this program, and I don't want to do that. I solved this as a programmer. But as a programmer, I can do it using brute force in a shameful way, or by using combinations that are reducing the number of tests. So what we are trying to do here is to show that this can be improved, and that these improvements can give you substantial improvement in performance without creating complexity of algorithmic solution. These all are 3 loops, nothing else. So 3 loops in one on another way. But if you have performance awareness, if you think about, is this good or not, you are immediately see that the first one here is not good. You cannot do so many unnecessary things without reason. Once you can immediately see that this can be reduced dramatically. So this is the fight against brute force approach. Now, there are many examples in programming where this is brute force, and therefore, let us avoid that. So I want to show you a couple of examples that do the same thing. The second one that is similar to your homework, and that was also used for exam in this class, was this one. You have an array of positive integers, like this one here, 3, 4, 5, 0, 5, 7, 1, 2. So this is an array of 8 integers. 8 or 8 million, whatever you want, has integers inside. Write the program that returns 3 largest numbers from here. So what are 3 largest numbers? The largest is this 7. That's the first one. Second largest is this 5. Third largest is this 5. Okay, so you have to return first is 7, second is 5, third is 5. So these are 3 largest. So the question is how to create a program that is returning 3 largest components in this array. How to write that program? So that the first is greater than or equal to second, and second is greater than third. So these are 3 largest. Okay, so an array of n positive numbers. What would be the worst possible way to solve that? Well, this is not difficult to find. You simply take this array and sort this array. 3 largest values are going to be at the beginning. So you sort the array, chop this first 3 and say, here is your result, enjoy. Of course, sort can be quadratic. For example, bubble sort. Sorry. Something is wrong. This slide went in the wrong direction. But anyhow, we have here the solution. So what I'm going to do now, I'm going to take this program, max3. I have the array A that has n components, and I'm going to return first, second, and third. These are 3 scalar values that are largest, second largest, and third largest. So what I'm doing here, I'm using select sort. I want this to be short. So I is going from 0 through n minus 1, and j is going from I plus 1 through n. So what we have, I'm comparing 0, 1, 0, 2, 0, 3, 0, 5, 0, n minus 1. Finding the largest value, putting largest value at the beginning, and then increasing this I by 1, and going 1, 2, 1, 3, 1, 4, 1, n minus 1. Finding the largest value, put it at the beginning. And then we continue that way till the end, sorted array. So this is select sort. If A of I is less than A of j, I have to swap them. So I have swap program 1 short swap program, swap this, and get the sorted array. Then first is 0, second is 1, third is A of 2. And here we have the results. Of course, you can do that even in a simpler way. You go to your favorite library, take from library the sort program and say sort array, and I'm going to give you first, second, and third. So put here sort and then return 3 largest. And that would be the most criminal way of solving this problem. First of all, of course, you have here that array is modified. But if this sort is quadratic, as this one here, then you are going to get a quadratic algorithm that is finding 3 largest values. The correct way of doing that should be this one here. So the wrong solution is sort the whole array with quadratic sort and give 3 first components. Correct way is go only once through that array and update 3 variables, max, mid, and min. So max is largest, mid is one that is less than is largest, and min is the third largest here. And then if you take any components, compare them with these 3, update these 3, when you come to the end, it is done. Now, this here, in my example with select sort is quadratic algorithm. This here is linear because you go through array only once. You have one single traversal. So before I do that, so I know that this is wrong. But I can say, you know what? I here sort the whole array. I sort the array that has 2 million components in order to get the first 3. How about if I put here aborted sort? I truncate this sort after I is 2. So when I go with I 0, I find the largest value, put it at the beginning. Then go to I is 1, find the second largest, and with I is 2 is the third largest. When I is 3, I don't care. I already have these 3 largest. So practically we have truncated sort. I put here I is 3. Don't execute this. This is the same program. Nothing is changed. And what I have in first part, I have n-1 tests. In second loop, n-2. In third, n-3. So how many tests I have here? How many ifs? I have 3n minus 6 such, which is O of n. It is linear algorithm. So I can wash my hands and say, this is linear algorithm, you have linear algorithm, and it is a good solution. Of course, this works, gives you 3 components, and it is linear. It is linear because we truncated it. But again, we modified the array. So array is now shuffled. It is not the same that it used to be at the beginning. And we went 3 times through the whole array to find first largest, and then second largest, and then the third largest. Can we go only once to make that faster? Of course we can. So the right way to think about that would be to have 3 variables called first, second, and third, where first is the largest, second is second largest, and third is the third largest. So since array is consisting of positive values, I have this array that has n components, and I'm returning first and second and third. And then where we have integer I index, I have the loop going from 0 through n-1. And then I'm taking this component A of I and saying, are you larger than my first component, which is the winner in this competition in this loop? And if you are, then I have to swap. So if I have the new first value, what has to be done? Well, I'm going to have the new first value. So first, this second has to be moved to third. And then first has to be moved to second. And then the new winner has to be sorted in the first. So if A of I is greater than first, then third is second, second is first, and first is A of I. And this is done. However, the number that I'm testing can be between first and second. So if it is not greater than first, but it is greater than second, then it is between first and second. Then I have to put second and third, and new second is going to be A of I. Then, if it is not greater than first, not greater than second, but it is greater than third, the only thing that has to be done, put new third. Third is A of I. And you go here once through the array from the beginning to the end, and we have that we create three largest values. If you remove this equality, then you have three largest different values, if this is the problem that we want to solve. So what is good here? The good news is that we are not modifying the array. Array stays as it is. So the information contained in the array is not ruined by shuffling, sorting, and something like that. It is unchanged, but we have the three largest values, and this is done in linear time. So it is a reasonable program. It is linear and gives me these three values, first, second, and third. You can ask the question, well, and what happens if numbers are not positive? So if they are such that I cannot put at the beginning here first is second, third is zero. Well, in that case, I have a little more complications. I have to put first three components in first, second, third. So put A of 0, 1, and 2. And then you sort these three components. So this is scalar sort. Scalar sort is always done with bubble sort. So if first is less than second, swap first and second. Is second is less than first, swap second and third. After this, the third is going to be the minimum value. Then go back first and second. If first is less than second, swap first and second. Now you have sorted. First is largest, second is second, and third is third. And now do the same thing as before. Now going from 3 to n, and you have this same shifting. And this is working in all cases, and it is a linear algorithm. So you can also make the program that is having here a minimum function, and then you put in the first and second, the third, the minimum of these three numbers. So when you go from there, you can, in this case, have a little shorter program and do the same thing as here. Now you have that they are minimum values, so if there is something that is greater, it will be stored in those locations, and this is going to be slightly shorter program. So it is short, it is simple, it is linear, and it works fine. So this would be programming solution that is acceptable. It has the same length as this here or this here, but this here is criminal, this here is linear, both of them are ruining the array. This here is working for positive cases, this is working always, and this here is working always, but it is short as possible. It is still few lines of code, it is still simple, but it is not shameful as the first one. The first one is showing a complete absence of brain when you write that. This is not the way how programmers solve the problem. Problem has to be solved in a different way, and the solution should be something like this. Another example, insert component X in sorted array A. This is the part of insert sort. So you have a sorted array, and you have value X that you want to insert somewhere inside that array. So what we have is integer array A, and this array has n components. So you put here n as an initial value. Then you have to insert this X in that array. After that, this n is going to be n plus 1, should be incremented, okay? So again, to insert this X in a right position, you can do that in two different ways. The first way is one that should be avoided at any cost. You simply say, I'm going to put this X at the end of array. So A of n equals x, and then increment A. So n. So A of n plus plus is x. And then I call my favorite sort program, A, that is sorting this array that has everything sorted by this bad value at the end. This is going to jump where the sorted put it, and you return that. So it has 2 lines of code. Beautiful. However, if this sort is a quadratic sort, then this insert is also going to be quadratic insert, what is not acceptable. What is acceptable is that you know that those things that are greater than x should be shifted for 1 position right, and then x should jump in its position. So this is going to be linear algorithm, and we'll have a minimum necessary number of moves to keep this array sorted. So array is sorted, and we are inserting new component in the sorted array. So what we have to do, as long as a of I is greater than x, we are going to say a of I plus 1 equals a of I. So we are moving for 1 position right. And we go that with I minus minus, decrement I, and going from right to left until we find the position when you have that this is not the case. If this is not the case, then a of I plus 1 should be x, and then increment n plus by 1, and you have done you have solved the problem. And this correct insert has 2-3 lines of code. It is appropriate, and it is not shameful. This here is shameful, and this here is a right way to solve the problem. You can sell that to somebody. It is a good program. Another example, yes, sir.
Wouldn't it be more efficient if you checked for the insertion, whether it's larger than the first half or smaller, and then you could just only insert on half the size of the array?
You can do that if you want, like in binary search, to find where is the position. So where is it? And then you go and move everything right. But it is questionable, is it efficient? Because whenever you have checks, you have to perform if statements. And here, and again, when you find a position, you have to move the whole array after that position right. So it is more or less the same thing. You always have to move the whole half array or whatever is part of array right for 1 position. So you are doing here step by step. You have to do that. You cannot omit that, even if you go with binary search to find the position. But you can do binary search. And the question is, what is going to be the number of ifs? Well, most likely with binary search, you are going to have smaller number of ifs because you always go half by half and find the position. So it might be a little bit of gain, but the program is not going to be simple like this, because you have this loop to perform always. When you find this position, you have to memorize what you have to move, and you have to move. And you have to put this A of whatever equals X. So this is always mandatory. On the other hand, the complexity of algorithm is going to increase. So you are most likely right. You get a little more complexity of algorithm, and you get few more microseconds. But this still, in both cases, remains O of n algorithm. It is always O of n because of this loop that is O of n. So I agree. You can do it that way and improve something. Is that okay? I guess it is.
Yeah.
So the power function, thank you. The power function, if you look how power function works in the library, power function, for example, if you have 2 to 8, you can compute that by multiplying 2 times 2 times 2, 8 times. So you have I is 1, I is less than equal 8, and then product is product times 2. So 8 times 2, you get 2 to 8, which is 256, and then return that value. But you have 8 multiplications. The power function doesn't work that way. It is practically taking this product 2, and then it is multiplying p is p times p. And then by doing that, you have only 3 iterations. Here you have 8, and they have 3. And practically the complexity is O of logarithm of n, not O of n, as you have here. Now, when you do that, also, if you have, for example, 2 to 9, then the power function comes to the closest power, like 2 to 8, and then multiply this by 2. So we'll come with this close to 2 to 8, and then we'll multiply by p. We'll have one more iteration. But again, you see that this is shorter than this here. So we are not going to do that, and we are not going to go into power function, but this shows that there is potential for improvement. I'm going to spend some time now discussing the problems of unnecessary type conversions. So this is something that is very, very frequent error that is made with programmers who don't understand exactly the way how numbers are stored in memory. And this is something that can easily be fixed, and let us go into fix that now. So data overhead, is the problem when you have different data types. So if you have one complex data type, like double, that is, and you have integer, you cannot perform operation between integer and double. You have to convert that integer to double and then perform operations between doubles. So compilers are inserting convert programs. So for example, numerical data types are signed or unsigned character, then short, then int, then long, float, double, long, double, etc. So this here is 8 bits, this is 16 bits, this is 32 bits. This is 32 bits, this is 64 bits, okay? And this is more than that, usually 80. So if I have in C, C++, or Java, similar languages, I have 1.23 that I write in this way. What is this? This is a double precision constant. So this 1.23 is written as sine plus mantissa that has 53 bits plus exponent that has 11 bits. So sine is part of that mantissa. So you have 64 bits that you have for this value. If you write to 1.23f, this is going to have not 64 bits, but only 32 bits. It is going to be shorter. Therefore, we have the reason to think, are we going to work with double precision number or single precision number? Of course, people who are lazy or don't understand that float does exist, they always write only with, do everything with double precision. So the first thing is, there are 2 data types, either integer or double. Well, that's not true. There are plenty of other data formats, and you don't use only integer and double and nothing more. Okay, maybe something more subtle is better. So length of integer, you have that short, which is 16-bit, is less than integer, which is 32 bits, and float is less than double, 32 versus 64. Now, data conversion rule is that you automatic conversion of simple data type to more complex data type. And automatic conversion consumes time and can be avoided by combining same data types. So you have that the order of conversion is character short, integer, float, double, long, etc. Short is the simplest, or character is the simplest, double is the most complex. So sometimes we use also 1 byte integers for various graph problems, etc. So here is an example. Let us say we want to compute 2 pi and run 2 pi equals 2 times 3.14. So is this correct or not correct? What do you think? Of course it is correct. Nothing is wrong with that. This is 3.14 multiplied by 2 is going to be 6.28. And this is going to be variable 2 pi. But you cannot multiply an integer that has 32 bits. It is 0, 0, 0, 0, 1, 0. That's what this 2 is. 1, 0, and zeros in front of that. This here has mantissa and exponent. You cannot multiply it in that way. You have first to convert this 2 to 2.0 to double precision number that has 64 bits and has mantissa and exponent. Hey, Pedro, what is the question?
Yeah, I had a question. So if you're writing
hey,
code,
let me just say something. Whenever you want, this is very polite that you raise your hand. Sometimes I don't see that. The simplest way, you just unmute your microphone and ask the question.
all right,
that
sure.
is simpler. Okay, go ahead.
Is this something that a compiler would optimize for you, or is it still something that we should be in the habit of, like writing, for example, 2 points?
There is no possibility to optimize anything. This cannot be optimized. You have to provide 2.0. If you don't provide, compiler will compile. But compiler is not a magician that optimizes something for you. There are things that are optimized. For example, there is a website called Nullstone, and you go there and you will find approximately 50 optimizing procedures that are built in compilers. Compilers have plenty of optimizing procedures, approximately 50 of them. And some of them are used, some of them are used when you say -02 or 03 or -OS. All this exists. However, nobody on this planet is going to avoid converting this to real. That's the tragedy. So the program should be written 2 dot times 3.14. If you write this way, you eliminate the program that is converting from 2 to 2.2 dot. And to show that, how this works, I'm going to show an example that will convince you that this has a point. So imagine the following trivial program. I have float A, B, C. These are float values. And I want to compute A is 2 times B plus C plus 1. So 2 times B plus C plus 1. It is written in this way. So what is going to happen? You are asking, what is compiler going to do? Here is what's going to happen. Compiler takes this expression here and says, first, I have to do multiplication because multiplication has higher priority than additions. So we'll take these 2 and say, hey, I have here double precision number, and A, B, C are floats. So this guy B is float. So I have to insert conversion from float to double. So it is going to library, taking the program that converts float to double. Now, float to double has to expand the mantissa and expand the exponent. So it is going to expand mantissa and exponent. This is the program that has 15 lines of code. We'll insert this program here. We'll convert B from float to double, and then we'll multiply double times double. We'll get the result that is double. So this guy here is double. Then it has to add new float value. And we say, hey, wait a second. I have to convert this float to double. So we'll again come and insert inside float to double conversion. And after converting float to double, we'll get double C, and we'll add this double and this double, and get this result that is double. Now comes the addition of this one. Sorry, folks. This here is an integer, and this here is double. You cannot add double of integer. You can add 2 doubles or 2 integers, but not integer and double. So this integer has to be promoted to double, and you have to convert this one, which is plenty of zeros with 1 at the end, to mantissa and exponent. And you have to create 53-bit mantissa and 11-bit exponent out of that. Somebody has to do that. This program that is doing that for sure has 20 lines of code minimum. So it increases, inserts these 20 lines, execute that, and get here double plus double, and result is correct. You have here finally 2 times B plus C plus 1. But this is double. Now, you have to store that in A, but A is defined as float. Therefore, compiler again says, oh my goodness, I have now double, and I have to store that in float. So brings the new program, conversion from double to float. Well, this guy here has 50 lines of code because it is more complex. The problem that you have now is that you have Mantissa that has 53 bits. Now you have to reduce that to 24 bits. So what you have to do? Well, in the worst possible case, you take the saw and cut and truncate a piece of bits that you cannot fit in Mantissa. But this is not going to be done that way. These smart programmers who write this will do rounding. So they are going to round the last bit of Mantissa. And if this is 1 and you have to round it to 0, you have to remove all these other bits up front. So there is plenty of bitwise operations over there that you convert double to float. Then you have exponent that has 11 bits in double, but in float, it has only 8 bits. So you have to see, can this fit at all? Because it can be huge that cannot fit. So you have to check, do you have error that you make when converting double to float? Because not all doubles can be converted to float. Only those that are smaller can be converted, big cannot. So most likely this is all going to work. But if you write this little statement, 2b plus c plus 1 as 2f times b plus c plus 1f, well, then you have that all these programs here disappear. There are none of them. So these are practically 3 different programs called 4 times. This disappears, this and this. And you don't see this anymore. Your program suddenly becomes fast and short. And this is the point in procedural programming. So if you write something like that, whenever we write something like that, we show complete ignorance of programming. That means having no absolute idea how programs should be written. This is not only wrong, it is shameful and demeaning for a programmer to write something like that. Absolutely unacceptable. Now you can say, who cares about that? These are 3 little programs. I don't care for them. This works in a short time. Raise your hand. Ricardo, go ahead.
So this is, again, one of those things that a compiler optimization would not catch then.
There is no optimization. There is no compiler. Somebody told you that compilers is magician and solve all your errors. No, no, no. Compiler is doing nothing for you. It's changing only a couple of things. But things like this cannot be optimized. Compiler is not, compiler that has no right to change your code. Source code, this is double precision. Compiler has no right to modify your double precision to integer. Because otherwise somebody is modifying without permission your code. That is rule number 1. I'm writing the code and compiler must compile what I have written. It cannot be that compiler will change my source code. If I put here dot, I want it to be dot. If I put here integer, I want it to be integer. Because if you permit this to be changed, then somebody changing your source code and you never know what happens. And compilers are stupid. Compilers are not humans. Humans are smart. They are going to do immediately this in no time. But compiler cannot optimize this. Compiler is doing here. And now comes the proof of that. The proof is this one. I'm going to take here variables that are in lowercase. A, B, and C is integer. Okay. And A, B, C in double in uppercase, A, B, and C are double. So I have A, B, C integer, and I have here A, B, C double. And then what I want to compute, A plus equals 2 times B plus C plus 1. Pay attention that this is double, this 2 is double, this B is double, this C is double, and this 1 is double. So no type conversions at all. What I do now, I have integers, and I have here 1 double with dot. So this is the same expression, generates same result, but it is I am forcing compiler to insert all these conversions. And you would say, compiler is going to optimize that. Compiler is be smart and put here not 2 dot, but put 2 without dot. No, compilers will never do that. Compiler is not permitted to do that. Okay, because I don't permit my code to be changed. I want this to be here to show you how stupid is this code and how regular is this code. Because when I multiply this, I'm repeating that how many? 10 million times to be able to measure this. So I'm measuring this time and this time. Runtime without type conversion, 31 milliseconds. Runtime with type conversion, 359 milliseconds. So this dot here costs me 11 times slower code. Of course, you can say, I don't care for this because these are milliseconds. Yes, these are milliseconds. But put this in all your programming style from now to eternity, and you are going to get that everything runs 11 times longer than it should run. So this is 31 milliseconds, and this is 359. And if you say compute plus convert divided by compute is 11.58 times slower. Hey, this is tragical. Okay. Then we go further. Change a different compiler, and you again have debug versus release. If you have release version, it is 31 milliseconds. If you don't understand difference between release and debug version of compiler, and many compilers are written that create debug version as default because they say you develop software, here is debug version. In debug version, this same program that runs 31 milliseconds, and this is, of course, Microsoft software, 187 milliseconds. So do you see what happens now? If I'm in debug version, I am 31 becomes 180. So this is 6 times or something like that slower. So without understanding the difference between debug and release, you have tragically slower program. And now, of course, because of debug, you are going to have the time conversions are going to have less effect, but it is still 1.75 times slower. So these things must be absolutely taken into account when you do professional programming. Programmers have to know these things. You cannot ignore that and think that is magical compiler, it is going to optimize everything for me. Nothing will happen. Nothing good will happen except that some things will, like 50 algorithms. Go to nullstone.com and look 50 programs that demonstrate optimizations that are made by compilers. They do plenty of things. For example, if there are tragical things like in loop invariant is written inside the loop, of course, you are not going to repeat some complex computation gazillion times that is not dependent on the loop. Compiler will take that, will make forward movement of that, will put a random auxiliary variable and put that in the loop. Yes, this is going to happen, but it is not going to change this tragical problems that I have here. Another thing that we also have as important problem is string to number conversion. So imagine that I want to read pi from the keyboard. So I have C in, this is keyboard, stream, and I want to insert from that pi. What I have to enter? I have to enter pi. So we enter minus 3.14, etc. Minus pi, I want to enter inside. So how many bytes I have here? 18, count them. 1, 2, 3, 4, 5, 6, 18. What is this one? This is ASCII 1. ASCII 1 is 49. Okay, so this is also 49, etc. So you have that this is a string of 18 bytes. Now, then there must be conversion program. Somebody who will convert that from 18 bytes to what? To double precision 64-bit mantissa and exponent. Somebody has to convert that. It cannot be stored in memory as 3.14. It's going to be stored as real number. So there is conversion program that is activated to convert this to binary double, sign, mantissa, and exponent. Now, that is stored in memory, and that's fine. Now, the conversion of string to double needs processor time. It is not coming from free. So let us now go in opposite direction. We want to display pi on our screen. So we say insert pi to output stream. We are not going to accept mantissa and exponent. Who needs that? So there must be a program that converts mantissa and exponent to this 18 bytes minus 3.14. Well, this is okay. This is legitimate. It should be that way. No problem with that. However, if I go and store this pi on disk, I have an output stream. Output stream, when I open file and I say file my data dot is called internally output stream, OS. So I am inserting this pi in output stream. What's going to happen? The same thing what happened here. It is going to take this value, will decompose that in the string and put this string in memory. So it is going to store pi as 18 bytes and not as double precision 8 bytes. So practically, you have that you are, hey, Saloni, turn off your camera, please, because we see everything that happens there. Saloni, please turn off your camera because everybody is seeing your camera. Okay. Just if you want, keep it. I'm not going to complain, but it is better that you, Saloni, Batia, turn off your camera, please. Okay, so the stored 18 byte string contains the same information as 8 byte double pi, and therefore uses 2.25 more times, plus twice conversion time to read and write. So this is not okay. If you have that your programming language supports binary file transfer mode, then it is much better than in this. So that is what is important. So let me turn this and okay. We'll do it that way. Now, going just a second. Let me. Okay, so now what happens when we have matrix operations? This is something that is very important source of possibilities to Saloni. We see your bedroom, we see you on the screen. Can you please turn on your camera? This is nicer reality show, but we don't need to see you in your bedroom, whatever are you doing now. So Saloni Batia, please turn off your camera or simply turn off your computer because you're obviously not listening this lecture. So performance issues related to matrix or array operations are this problem. You can have either row-wise or column-wise storing of matrices. So if you have row-wise, you have languages like C, C++, etc. They have row-wise the way how this is done, or languages that have this column-wise. So if we have row-wise, then we have that written in computer standard. If we have column-wise, we have that also written in computer standard. So what we have here, unspecified way, which is done in Pascal or BASIC. You have no way how is this done. So in this case, compiler designers select the storage method. So it is not row-wise, it is not column-wise, therefore it is unspecified. Now, what can happen if we have differences between row-wise and column-wise? If we have row-wise, we have first row, 1, 2, 1, 1, 1, 2, 1, 3, followed by the second row, 2, 1, 2, 2, 2, 3. If we have column-wise, you have 1, 1, 2, 1, and then second column, and third column, and fourth column. This is written in the standard of language. And therefore, if we have that we process arrays, we can go in two ways. We can go sequentially, byte by byte, through memory. Or we can go jumping through memory in a wild way. Now, if we go sequentially, we use register auto-increment addressing mode. You put the address of the beginning of array in register, not what compiler is going to do. And then when you go to next component, it is simply going to put one clock pulse to that register, will increment by 1, and in no time you are going to have the address of the second component. It is going to be very fast access. If you jump through memory, if you go from A of Y to A of J, then what you have to do, you have indexed addressing. Therefore, you're going to have here address of the beginning of array plus index times the size of component, and then you're going to compute effective address where you have to jump next here. This is index addressing. You have access to memory location where you have the index, and you have to perform operation of multiplication and addition. And so this is going to create overhead and be much slower. Addressing mode is either efficient addressing mode in memory or inefficient with indexed addressing. So that's the problem. When you have sequential access, you are going to have better filling of caches. If you go multiple times through that, you are going to have everything in the cache, and therefore it's going to be much faster. If you have huge arrays, if you go sequentially, you are going to have less frequent page faults, and this is going to be faster also. So addressing mode, caching, and paging are going to be better. Now, if you have this improvement, you can also say, if I have a matrix like M of I, J, and K, I have 3 indices. Now, this I is first index, J is second index, K is third index. But they can come in any order. The order doesn't tell you that this I has to be first. It can be third. So you can do any permutation of that. So let me show you an example. If I have to have matrix addition, if I compute sum of components in a matrix, I can have loop from I is 0 through n, loop from j is 0 to n, and I say sum plus equals m of ij. This is going row-wise, first row, second row, third row, fourth row, etc., etc. If I go column-wise, m of ji, this is the same program. Everything is the same, except that I permuted these two indexes. Said now j is the first index, I is the first index. And again, I am computing the sum of components of the matrix. Now, when I do that on this with Visual C++, again, Microsoft compiler, if I go row-wise, this is going to take 29 seconds. When I repeat that sufficient times with 500 times 500 matrix. If I go column-wise, 98 seconds. I have that this is 3.3 times slower if I go column-wise, okay? So obviously, one permutation of indices gives me 3 times improvement, which is dramatical. If I take the same computer and switch to GNU compiler, G++, and take third level of optimization, row-wise, 9 seconds. It used to be 29, now is 9, 3 times faster, okay? And then you think column-wise is going to be spectacular. Yes, it is spectacular, 136 seconds, which is 14, almost 15 times slower, okay? So if you compare this example in the case of this particular adding of components of matrix, I can go from 9 to 136 seconds. And this is dramatical. Now, you can say, okay, is this something that happens always? Yes, it happens always. Look what happens in matrix multiplication. If I multiply these two matrices, C is A times B, I have three loops, I, J, and K, and I can make any permutation of these loops and any permutation of these indices, I, K or Ki. If I do that, I have here 8 possible permutations of indices, 2 here times 2 here times 2 here, and 3 factorial 6 permutations of these loops. This gives me 8 times 6, 48 different ways how can I write this program that multiplies two matrices. And I know up front that these are 48 different traversal patterns of data in memory. One of them is the fastest. Which one? Well, perform the measurement. And here we go. You have that this is the worst one. This here is the best one. So our job is to find the best one. Which one is the best permutation? Because the differences can be 10 times in the same program. Ricardo, you rose your hand, it seems to me.
There was a pattern, I forget which class, I think it might have been operating systems, where you would just multiply by column, which would be the fastest. Since if you're multiplying the matrix by each column, the axis is much lower. So you're just iterating through the columns doing the multiplication.
Well, there is no way to do it immediately. 48 different ways how to do that. And one of 48 is the fastest. So this one here, you can see which one is the fastest. The fastest is IKJ loop. IJK is the loop that is going the way how you compute scalar product row times column. This is one that is written in linear algebra textbook. This is 2.762 times slower than this best approximation. But then you can improve that by doing permutation of indices. So there are 48 different memory traversals, and you see all of them here. This was because no time. I did it in a little faster way. But if you are interested to see that, there is a paper about that published, and you will see that the difference between worst case, which is this one here, and best case, this one here, is 10 times. So it is dramatical. And matrix multiplication is something that happens each and every way when you have anything that is graphical. So you cannot write matrix multiplication program in this way. You have to find in your architecture which one is the fastest. If you have written in this way, it is going to be still possible to improve it 3 times by making permutation of these indices or permutation of loops. If I permute loop I and J, put first J and second I, it is going to compute the same thing. Do you agree with that? If I put first J, second I, is this the same program or not? Yes or no? You are not convinced, it seems to me, but it is the same program. So the simplest thing is, don't do anything else. Just permute J and I loop. First J as the first loop, I as the second loop. It is going to do all these combinatorics the same way. But the memory traversal will be different. And there are 48 of them, not column times column. It is row times column. That has to be done. But again, there are 48 ways how I can do that. And one of them is the best. And the best is this one here at the bottom. Okay. The worst one is this one here. And here in the middle is somewhere one that is mathematical, linear algebra, row times column, scalar product, put that in C of ij. Okay, is this the answer to your question or something else you want to have? or comment. Disagree if you want. This is done, by the way, under Ubuntu Linux. This 48 versions of matrix multiplication from best to worst. You are not going to find this best without measurement. There is no theory that is going to give you this one immediately, because you can have different languages, different optimization of traversal, different addressing mode, different caches. Everything is different when you move from machine to machine. There is no way you are going to find this one by using any kind of theory. You have to measure. And this is how programmers do optimization, do the measurement and then write knowledgeable code. If you have that the problem has a robotic arm that moves, or that you have graphics that needs permanently matrix multiplications, you have to do such measurement if you want to improve the speed. And it is not too expensive. You said, sit down one day and find what is the best for your architecture, and then you find it. And that's it. That's what procedural programming is all about. This is the programming solution of matrix multiplication. This here is mathematical solution. But programmers are not doing things mathematically, are solving problems as programmers. And therefore, there is the worst case and best case, and I want to find the best case. Any comment? Question? Okay. So that's it. Thank you. Wilson.